In the previous 3 sessions, we have learned about general linear model for longitudinal data. We have seen how to use the weighted least square estimates or how to compute the weighted least square estimates as well as the ReML estimates for the parameters involving in a general linear model. In this session, we would be using R to demonstrate the weighted least squares and the ReML estimates, as well as we would also use the simple technique of OLS and see how it differs from the weighted least squares and the ReML estimates. We shall be using the Sitka data. The Sitka data was introduced in the first lesson for the general linear model. We shall be using that, and using that data set we would be first applying the ordinary least squares, then the weighted least squares, and then the restricted maximum likelihood. But the restricted maximum likelihood in R is used using the generalized GLS, generalized least square idea. So we shall see all of this, we shall learn about the packages, and we shall see how to perform this on a real data set. So this session would be absolutely hands-on in R. We would be applying general linear model on a data set in R, and the data set that we would be using is the Sitka data. Note that the Sitka data consists of measurements of 79 Sitka spruce trees, of which 54 are grown in ozone enriched chambers and 25 were treated as controls. The size was measured 5 times at roughly monthly intervals, and the data is complete and balanced. There is no missing data, and each tree is measured 5 times and is available as Sitka in the R package mass. Now, what is the objective? So, the hypothesis that we want to test here is to check whether the effect of ozone and control is different for the growth of the trees, the growth being measured by log size. So formally we can write the hypothesis as mu j under ozone, that's the mean growth under ozone for the jth time point, is equal to mu j control, that's the mean growth under control for the jth time point. J runs from 1, 2, 3, 4, 5. One way could have been that we could fit models treating that growth is a continuous function of time, and we would be doing that in the later part of this series where we start modeling the Sitka tree under marginal models and under linear mixed models. But here we would treat time as a factor. So that means for each discrete time point we are testing whether the means are equal or not, and we have 5 time points. If we want to start off with the analysis, we need to explore the data. This exploration has been talked of in details in the second and the third module of this session of this longitudinal data. So we need to call in library mass and library lattice, library mass for the data set and library lattice for the XY plot command. And if we see once again a brief idea, we are seeing that the control trajectory is a bit higher than the ozone trajectory, and we can use the Pierce plot. Again, the details has been discussed in the first session of general linear model. And once we use the Pierce plot, we can use the Pierce in context to the control. And in the next slide, we have the same plot for the ozone group. And we see that for each discrete time points, the data is correlated. So if we find the correlation between the individuals for two given time points, but that correlation is pretty high in the order of 0.9. But with a trend that the correlation over time is decreasing. So the natural question is whether we need to use a exchangeable correlation structure or a year one model, and we would see what fits in best and how do we go for that. For the ozone group also the correlations are pretty high, except that for time 1 and time 3, 4 and 5, so with increase in time the correlation is tipping a bit, but that again is not a very conclusive evidence of whether we are going to fit a year one or an exchangeable correlation structure. Now to start off with, let's summarize the observations. The first is that there is difference between growth of log size for trees between the control group and the ozone group. Also there is individual level heterogeneity as indicated by those black lines in the two panel plot or the XY plot that we used. The log size measurements are pretty highly correlated, and to start off with we assume that the correlations are weaker, which is indeed a fact, as the difference between measurement occasion increases. So we would be assuming a ER1 type of a structure. So to do the analysis, we start with importing the data. Now we have already imported or rather we have already called the library mass. Now if we write head Sitka, it gives me the data. So the first 6 rows with size as the log size, time, that's the time in days, tree and ozone. The first thing that we do is convert time into a factor. Now to do that we make a copy of the original data set. It's always better to keep the original data set as it is and make a copy of it. So we copy it into another data set again called Sitka, but this time the S starts smaller, and since R is case sensitive, capital S Sitka and small s Sitka is different. And we would be working with the smallest Sitka data set, and from here what we can do is Sitka $time, and we say it to be factor, and the names of the factor is T1 to T5. So we can use the paste command in the labels option, and then the levels of Sitka $treatment is ozone and control in full. So we just want to change it to CTRL and ozone so that everything fits in the output window. And the first thing we do is we start with the simple ordinary least squares. So we use, say, OLS1 is the object, LM, size explained by time into treatment. Note that treatment is time is here discrete. So basically we are seeing the effect for each of the 5 time points, the intercept being the effect of time T1, and then the effect of time T2. A difference of the effect time T2 is given in time T2, and then the difference of the intercept from time 3 from the intercept or the first time point is given. Now what we find is the effect of the time, the differences are all significant, but that for treatment there is no significant difference. So for the first group, so for the time T2 group is different, and treatment ozone doesn't have a significant difference. So it says that there is basically no difference between the treatment group and the ozone group. Only thing is that for ozone all the coefficients are negative, meaning no significant difference. So if we run an analysis of variance table, we can find that same thing. Time into treatment, there is no effect. Now to implement the robust estimation or the weighted least squares, we need the GEE package. Now for the GEE package, we need to first install GEE package and using the usual commands, and then library GEE, and then GEE1 is GEE size explained by time into treatment. Again the same thing, but this time we are specifying a few things, and the first thing that we are specifying here is ID equal to tree. That means we are specifying that there is a grouping by the IDs, and the grouping IDs are the column called tree. Now GEE object produces a lot of things. To have a idea about what it produces, we can use names GEE1, because GEE1 is the object name that we have given to the GEE object, and it produces a lot of things, so title, version, models, calls, but the important things are coefficients, working correlations, and we would be extensively using GEE for marginal models, and we would see how we can use that. We have not specified anything, and here the GEE $1 working correlation, that's the W matrix of the WLS, comes out, it has been taken to be diagonals. Now let's see what are the coefficients. So if we go about summary GEE $1 coef, comma 3. So basically what we have done is we have taken summary of GEE $1 the coefficients, and we have rounded it into 3 decimal places so that it fits in the window. We get the estimates, and GEE1 or the summary of GEE1 doesn't produce the p-values, but we have the naive standard errors as well as the robust standard errors. So we have the naive Z and the robust Z, and we can use to test for the significance of the estimates, which is done later. Now the comparison between OLS and robust estimation. So we have already done the OLS using the LM function, and the robust estimation using weighted least squares through the GEE function. Now we want to see the estimates along with their standard errors side by side, and so what are we seeing? So to do that, we need the library textreg. Again, it's a very useful function to print models, different types of models with the same response, and then we are using the screenreg command, list OLS1 or GEE1 single dot row equal to true, means it prints the parameter estimates and the standard errors in the same thing, and then we are talking OLS and WLS for the LM and the GE models, and we are giving stars for estimates which are significant. The significance is assumed at p less than 0.05. And another advantage of using this textreg is that if we use the GE which doesn't give the p-values, this computes the p-values and indicates whether it is significant or not. Now what we see here is that for the intercept all of time, the OLS and WLS, there is not much of a difference. What changes is the standard errors. If we see, in general, the standard errors have reduced, particularly in treatment ozones, because the OLS said that there is no interaction effect between the treatment and time for treatment ozone, while weighted least square says that there is some effect, at least for the 4th time point and for the 5th time point, and that effect is reduction, and the reduction is significant. See how the standard errors have reduced from 0.22 to 0.08. So previously we had not specified the correlation structure or the working correlation matrix, and it had by default taken to be independent or I. Now suppose we want to use correlation structure to be exchangeable, or suppose we want to use the correlation structure to be AR1, What we can do is we can use the CORSTR, that's the construct option, and specify it as the construct exchangeable or ARM, and so we have GEE2 and GEE3 as the two objects, and then we can use summary GEE2 and summary GEE3. I have not printed out the results of summary GEE2 and summary GEE3 because it produces a lot of things, but the interested user can do that. Interestingly, let's see what the correlation structures or the estimated correlation structures it's coming out to be. So when we say that GE2 has a exchangeable correlation structure, we see that the value of rho comes out to be 0.92287. So that's 0.923. And that's the correlation assumed between any pair of observations for a given individual. But here, if we say working correlation to be ER1, then we start off with correlation to be 0.96 between the first, and then the correlation decreases with every increase of separation. So with every time separation increasing, so between first and second is 0.95, between first and third is 0.91, between first and fourth is 0.87. So for a distance of 3 time points, 1, 2 and 3, we are getting 0.87. So that's how we get the working correlation estimate of the working correlation structure. Now, as we all know that weighted least square does not make any assumption about the likelihood, and we have also learned theoretically about the ReML functions. So we would be now using the R package NLME to compute the ReML estimates. But ReML estimates does not provide the sandwich standard errors, which generally the weighted least squares provide. Now, to do the ReML estimates or to do the maximum likelihood estimates, we would be using the GLS function in R package. The R package NLME contains the GLS function. So we call library NLME, and then we use the same model GLS1, GLS2 and GLS3. Note that it's the same model as GEE1, GEE2 and GEE3. The only difference is that here the correlation structures are same. So for GLS1 and GLS2 it's the same. The difference come in form of, for GLS2 the method is maximum likelihood. For GLS1 it has not been said anything, so the method argument if not specified means the restricted maximum likelihood estimates. GLS3 we take a different correlation structure. The main difference between GLS and GEE is that GLS computes things from the likelihood, the parameters or the inferences are based on likelihood, while for the GEE it's, or rather if we use the weighted least squares using the GEE function, it's not, or the parameter estimates are not from the likelihood but from minimization of residual sum of squares. So we can use, to make a choice of the models, we can use the ANOVA function. So ANOVA of GLS3, the denominator degrees of freedom comes out to be 385, and we see that the p-value for time into treatment is 0.0175, which is significant. OLS didn't report significant, but GLS3 is, or the GLS is reporting that the interaction between time and treatment is significant. Also, I can use the ANOVA function for comparing models, so GLS1 and GLS3. So if we have to choose between exchangeable and ER1, which one is the one that we should choose? Definitely we are going for GLS3. Reason? It has a lower AIC or a higher log likelihood. And to find the confidence intervals for the coefficients, what we can do is we can use the intervals command. Now these are functions for NLME functions which are general multipurpose functions, and if we use the intervals command, what it produces is it gives for the first set of coefficients. So we are using the intervals of the coefficients and not of the variance components. It is giving the estimates along with their confidence intervals. If we use 2, 3, so it gives the correlation structure. So the what happens to phi and what's the correlation, what's the variance component for sigma, and what's the standard confidence interval of sigma, and all those things. But let's have a comparison of the three. Now let's see again the screen rec function that we would be using. Now with this we have OLS, WLS and GLS. Now what are we getting? We are getting, in terms of parameter estimates, we are getting nearly identical results at 2 decimal places, but the standard errors are changing. In general, the standard errors of weighted least squares and GLS is much less than the standard errors of OLS. Further, GLS has even lower standard errors as compared to WLS. So let's see what we are getting from the three models. For both WLS and GLS, the correlation structure was specified as AR1. Now the interpretation of the coefficient is that for the time factor, time ti, I equal to 2 to 5, it represents the difference in log size from the intercept, while the intercept here is interpreted as the effect at time t1 for the control group. The coefficient of treat O's is the additional effect of ozone in log size for the first time point in the control group, and the interaction terms here is the additional effect of ozone for each of the time points, that's the second, third, fourth and fifth time point. Finally, what do we see here is that except for OLS, both WLS and the ReML, that's the GLS, is telling that for the fourth and the fifth time point, ozone is suppressing the growth, and this suppression is a significant suppression. So that means ozone really is having a retarding effect on growth, particularly if the trees are exposed to longer time points into a ozone rich atmosphere. In this session, we have done a practical application of the general linear model, where we have taken a data set and have analyzed the data set, first using ordinary least squares, then using the weighted least squares, and then using restricted maximum likelihood estimation techniques. The data set that we had taken is the Sitka data set in the mass library, and once we have taken that data set, we did the ordinary least squares, which showed that there was no difference between ozone and control, while the weighted least squares and the restricted maximum likelihood technique or inferences drawn on the basis of the ReML technique showed that there was significant difference in growth, and in fact ozone suppresses the growth of the trees or the Sitka spruce trees. From the next session onwards, we would be starting with the linear mixed models for longitudinal data. Now note that we had assumed that time to be discrete, but now from the linear mixed model perspective, we would take time to be a continuous entity, and we would see how to model or how to introduce the correlations using the linear mixed effect model technique.